which structure helps explain why the aniline ion, shown here, is a stronger acid than is ammonium ion over here, right? Ammonium, aniline, right? And it's good they just give us something like aniline, so we don't have to know, you don't have to be able to draw aniline ion in order to determine this problem. It's given to us. So usually ACS won't trip you up on stuff like that. So how do we determine the strength of an acid? First of all, we draw its conjugate base, and we'll determine how stable its conjugate base is, right? So the idea with acid, right, we can draw out equation for an acid. We take an acid, we put it in water. Let's just draw it like this. We put an acid in water. We'll leave out the water. And all it does is it donates a proton. Basic definition of an acid. So the idea is the more stable this guy is, the less it's going to go back over to its acid form, right? All acids are in equilibrium, just for strong acids, this equilibrium favors this side so much because this guy is the most stable, right? So the stability of the conjugate base over here will determine the strength of this acid, okay? So we want to see, well, what would this conjugate base be? If we donate a proton, what would we do? Well, let's draw this guy like this, right? And so donating a proton would go here, okay? So now, back over to this side, what we have is, after donating that proton, this, NH2, and we picked up a lone pair here, right? So this is the conjugate base of the aniline ion. Now, so why is this guy so stable? Well, how can we show stability? The more resonance forms a structure has, the more stable it's going to be. So let's see if we can draw some resonance here. Right, this is a lone pair, so we can move it. If we move it down here, we got to delocalize this pi bond. So let's move it over here for the first one, right? Okay, so that's one of the ways we can show its stability. So let's see, we got a double bond here, NH2, put positive charge here, right? And we could keep moving this charge around, right? We could go like this. But let's pause here for a moment and let's go through the answers. Okay, so first of all, A and C show the acid instead of the conjugate base. B and D both have NH2 here. So they're showing the conjugate base after we donated a proton as an acid. But this guy, let's see, well, we should have a neutral charge after we donate this proton. This just has a minus charge. So we picked up an extra electron in D. So D is not a correct resonance form. You can see that B is exactly this molecule here. Right? This is B. So B is probably our answer. Let's look at A. Okay, so A would be, let's see, this started off here, NH3, positive charge. So, let me see, that'd be if we moved it around. That'd be, well, let's start from here and try to get A. Okay, so this was NH3. So if we went up here, right, we just get A. But what's wrong with A is that this N is bonded to 3 H's, right? So this N has 5 bonds, has 1 double bond and 3 single bonds, so it breaks the octet rule. So that's no good. Alright, C. Let's see how we got what they did with C. Let's see. Well, positive charge, we threw on a lone pair of electrons because originally we started what? We started with, we had this originally. So yeah, we could go here and then we get rid of this mucking up the board here, but we'd get a double bond here, and just single bond over here, right? And so we get rid of that positive charge up here and put a positive charge here. And so now for C, they just threw in a lone pair of electrons out of nowhere and added a minus charge. So that's not what's going to happen. So right, we can cross off C. We proved that one wrong, and we're left with just B. And hopefully it made sense how I showed the conjugate B as a conjugate base, a resonant form of the conjugate base. Okay.